So hi everyone and welcome to the 11th TIA Centre seminar of the academic year. For those that are new to our seminars, we invite researchers and leaders in the areas of computational pathology and associated areas to discuss their work. And today I'm delighted to introduce Zhilong Weng. Zhilong is a PhD student at the University of Cologne and the University Hospital Cologne, supervised by Yuri Tolka. He got his master's degree in computational engineering from the Technical University of Darmstadt in Germany, where he focused on computer vision research, including traditional image processing and deep learning-based image detection. His current research focuses on advancing AI applications in computational pathology. The title of the talk today is GrandQC, a comprehensive solution to quality control problem in digital pathology. So Zhilong, thank you again for joining us. It's great to have you giving a talk. So whenever you're ready, please feel free to start.
Okay, thank you. Also, Okay, thank you. Hello. Thank you again for this opportunity, and it's a great honor to present my work here. Again, my name is Zhilong Weng, PhD student at University Hospital Cologne and University of Cologne in Germany. And today, I will introduce my quality control tool, GrandQC, a comprehensive solution to quality control problem in digital pathology. In pathology, we work with the slide, and these slides are full of artifacts. There are many ways how the artifacts appear, most of them due to tissue processing, and also some of them from scanning. And the examples are shown in this slide. Now comes a question. Why should we pay attention to these artifacts? Because artifact problem is a challenge for AI algorithms, and AI algorithms fail when they miss artifacts. For example, here, this table is about false positive caused by artifacts. Here, we use two segmentation models to test 105 regions of interesting image from long slides and 33 regions of interesting image from long slide. From this table, we can see that some image mistakenly shows artifact as tumor, such as in 14 images from long slide, tissue folds are incorrectly detected as tumor. To clearly show how artifacts affect tumor segmentation, here I also prepared some examples. These are about pen mark and tissue fold. The first image is original image, and the second one is the result from tumor segmentation model. Blue in the second image here means false positive tumor detection. We can see that some benign tissue under the pen mark is falsely detected as a tumor, and the tissue fold has the same problem. So if we could have a good quality control tools, such as our GrandQC, we could detect and mark them, like here. And here is another example related to out of focus. The original region of interesting image is the one without out of focus. And when we apply the AI tool to it and compare the result with human annotations, we got good accuracies. However, if we add an out of focus area to the image and apply the same AI tool, some tumor and tumor stroma area are falsely detected as mutant. By using our GrandQC to identify artifacts, we can mark those areas and accurately assess the AI tool's true performance. Here are two tables. Here are two tables showing how out of focus artifacts affect the performance of AI tools. We first apply AI tools to a data set and obtain the baseline results. Then we add out of focus area to the data set and apply the same AI tools and recalculated the results. As expected, the dataset with out of focus have much lower dice score and sensitivity. This means that accuracy has decreased and false positive has increased. Finally, after applying GrandQC to detect and mask the artifacts, the result improved significantly and were much closer to the baseline. So quality quality control tool is important for other AI algorithms in digital pathology. Yes, and currently there are some QC tools available. For example, Histological. Well, they have been helpful, and but they also have some limitations. Some of them cannot detect all types of artifacts, and some QC tools are based on traditional image processing, which have low accuracy and cannot be used directly. Some QC tools require uploading image to their server, which involves medical data privacy. And there are also some other limitations. To address this issue, we developed our GrandQC. Here, I will present the comparison between GrandQC with other QC tools. And all QC tools are based on their default settings. First one is our GrandQC, followed by HistoQC, PathProFilter, and HistoRI, which are all very popular QC tools. The first example is about tissue faults. GrandQC can detect all tissue faults, even very small ones. And HistoQC use traditional image processing and focus on finding useful parts of the images. It can detect tissue faults, but we can see here it over-detects, causing loss of important information in one slice. And both pathology and HistoRI use path classification to identify artifacts. And in this example, pathology detects tissue fault location, but with low accuracy and under detection. HistoRI, on the other hand, has too much noise points and over detection. And the second example is about air bubble. GrandQC can accurately segment the air bubble area at the pixel level, even for the complex air bubble boundary. It can identify them with high precision. And here, we can also see how other tools perform in air bubble detection. HistoQC, again, over-detects. It lost too much information, and PathProFilter cannot detect air bubble. Histo-RI can detect the air bubble as well as the boundary, but there are too many noise points. The next two examples are groups on slide and PEMARK, both of which GrandQC handle well. GrandQC and Histo-RI can identify growth areas, and HistoQC tends to consider the whole slide unusable, and PathProFilter can identify growth boundary. For PEMARKing, HistoQC and Histo-RI can both identify it well, but they both ignore the small PEMARKing with lighter color in the middle, such like here and here. So, and pathProFilter cannot detect PEMARK in this slide. And finally, GrandQC supports local deployment, allowing up to run it offline and keep medical data privacy. And now I will introduce how we develop GrandQC. For GrandQC, we have two tasks: tissue detection and artifact detection. First, we use a large manually annotated training dataset. It contains slides from multiple organs and multiple institutes. Further, we create a very special large test dataset. And this test dataset contains the slide from 4 different organs. We ask the lab technician to reproduce all the artifacts, and we scan the slide and annotate them. And this is how we train our algorithm. Both tissue detection and artifact detection algorithms are pixel-level segmentation algorithms. For tissue detection, we use 1x magnification. Therefore, it's very quick. And for artifact detection, we use 3 different magnifications. There are 5x, 7x, and 10x magnifications. These allow nice balance between quick analysis and more precision. And here is an example. We use tissue detection to detect tissue areas and 3 different versions of artifact detection to detect all artifacts. And here is more information about the algorithm. At 10x magnification, more artifacts can be detected, and the dice score is higher, but it takes more time. Compared with other magnifications, 10x magnification is more sensitive to out of focus and can detect more out of focus area. At 5x magnification, the dice score is lower, but the processing is faster. The following table, this one, shows the running time of tissue detection and artifact detection on 2 different types of slides. The speed of tissue detection and artifact detection depends on the type of slide and the hardware we use. All our tests were performed on a standard personal computer with NVIDIA RTX 3019 with 24 gigabytes and without any inference parallelization. We can see that since tissue detection uses 1x magnification, it runs very fast. For a single slide, the average running time is within 1 second. As for artifact detection in general, the larger the magnification, the longer the running time. The average running time for a single slide is within 1 minute, and the choice depends on the actual needs. And here is another example of whole slide image processing. Here you can see what artifacts the GrandQC can detect. There are air bubble, slide edge, pen marking, out of focus area, tissue fault, dark spot, and foreign objects. Here are further examples. For GrandQC, we perform a large validation. For tissue detection, pixel level accuracy was very high. Next, we perform a real-world validation. We took data from 5 institutes scanned by 5 different scanners. 2 independent reviewers analyze this slide. They provide the quality of tissue detection using a scale from 0 to 10. Both estimated the performance as nearly perfect. And then is artifact detection. Firstly, we use our independent multi-organ test dataset. Again, the pixel-wise accuracy of 3 different magnifications were very high. Next, we made a large-scale clinical validation. We saw that GrandQC is a powerful benchmark for pathology institutes and scanner systems. It allows real-time QC monitoring in pathology department. Here is how large the clinical validation is. We run the GrandQC on material from 19 different departments from many countries. Here we can see the area with artifact in single slide in different departments. Based on this result, we put all departments on this slide according to the quality. As you can see, the quality is very different. And if I am a new department, I can make a test with GrandQC and see where my play on this slide is, how good my quality is. We can make a deeper analysis for different artifact types and see where is the problem. GrandQC can help pathology department improve their ability to prepare slides. Now we use GrandQC as a benchmark for scanner system. We scan the same slide by 2 different scanners and compare the quality. Let's look at the out of focus. This one, scanner 2 produce much more out of focus region than scanner 1. So now when I am going to digitize my department, I can use this to compare all scanner systems to see which scanner is the best for me. We made the same analysis for TCGA dataset and generate the mask. So we have open sourced them also the whole GrandQC tools and our test dataset to radically solve the QC problem in pathology. And if you are interested, in GrandQC, here is our paper. We published it on Nature Communications, and here is related GitHub project, where you will find a detail to show how to use it. We have also uploaded all the models, including tissue detection models and 3 artifact detection models. And the test dataset we use, the quality control mask of TCGA datasets to this database, Zhilong. And all relevant links can be found in our paper. And if you have any question, feel free to email up. And that's all. Thank you.
Well, thanks, Zhilong, for a really fantastic talk. So, and I think this is a really fantastic, a really great tool. We really need these QC tools in our community. So it's great to see that more of these tools are becoming available. And yeah, so we'll open the floor to questions then. Does anyone online or in person have any questions they'd like to start with? Brilliant. Well, one of the questions that I had while I was listening to your talk was that you've obviously validated this tool quite extensively across different data sets and across various different sites. I just wondered if you could elaborate a bit more on, in terms of the training, were there any particular domain generalization techniques that you employed to ensure that your model was robust on the testing data?
Sorry, could you repeat the question once more time?
Yeah, of course. So you validate your model on loads of different sensors, which is fantastic. I was just wondering, in terms of the training, are there any particular domain generalization techniques, such as stain augmentation or stain normalization, that you employed to make sure that your model generalized?
Actually, during our training, we didn't use any stain normalization because since our training data set is large enough, so that's why we didn't use it.
Okay, sure, thank you.
Maybe I can shortly add to this. It may be not a general response or a specific response to GrandQC, but to any other tools we develop in the lab. Basically, we started 3-4 years ago with using stain normalization, like typical Masenko approach and so on. And actually, after a certain point, I think it was when we saw the paper from Nijmegen from David Tellers, if I'm not mistaken. So it was actually 2 studies. The first of the studies was very systematic test of different data augmentation methods. And they suggest this typical data augmentation method with brightness, contrast, hue, and saturation, and so on. And after that, we employed this method. And actually, we never saw, most of the data sets we use are in such a large range. So we never use like 10, 20 slides. And we saw that actually we don't need any stain normalization. And all the problems are solved with a data augmentation. So we use it not in very aggressive mode, so according to Tellers and co-authors, but more in such a moderate mode. But it solves most of the problems with generalization.
Okay, no, sure, that makes sense. Okay, fab. Well, we've got another question online from Craig. I think he said, "Great talk. I can clearly see how this will be helpful for in pathology labs. I'm wondering if there has been any assessment on whether these tools help in downstream tasks." i.e. removing the artifacts before feature extraction, results in better model performance. Did you get that question? Sorry, Yuri or Zhilong?
Yeah, maybe
Yes.
I can. Maybe I can take the question. So actually, we in the first implementation or in the first submission of this manuscript, we did not do this analysis, but then there was a comment, I think a very important comment about this real value of such tools in the downstream tasks. And then we looked, I think it was several slides Zhilong presented in the beginning of his talk. Like we tested it for several tasks, like for tumor detection, for segmentation, also for single cell detection, and we found that actually in most of the tasks, or in each of the tasks, there was a very clear benefit. I mean, it's probably something very obvious, because if you work with such algorithms and analyze the slides, both in a research mode, but also in the clinical routine, when you use some commercial algorithms, for example, you see immediately how the algorithms make mistakes in regions with artifacts, like with faults, with autofocus. So basically, it was a very this validation we did to address this issue was like a very small validation. So we did not use any multi-center cohorts, because it was pretty obvious for us that it should help in any of the downstream tasks. With regard to this specific aspect, like how the features look like if we extract the regions with bad quality, I don't know. So probably they look better if you are speaking more about such prognostic applications and so on. But it's very on all diagnostic tasks like detecting objects, there is a clear benefit of implementing a QC step before downstream analysis.
Yeah, definitely. Thanks, Yuri. No, thanks for a great question, Craig. And I also had a question in terms of, so on one of the last slides, it was showing the different magnification. So it said that for 5x, there was, I think it was a dice score of 0.94, and then it lowered slightly for 7x, and then for 10x again, it was slightly higher, but a bit lower than at 5x. So are we just finding that 5x is the best model, and that you recommend just to use 5x? It's quicker, it's better. Is that the outcome?
I think our choice for now, for our own projects, is like a 7x model, because it's like basically the same quality or the same accuracy as 10x model, maybe slightly less, but it provides a very nice trade-off between speed of analysis and accuracy. I would not recommend to use 5x if computational resources and time allows that. So I think 7x is probably the best. I think we also said this in our repository at GitHub. I also wanted to mention one thing. So actually, we have in the algorithm two different models, one for tissue detection and artifact detection. And when we analyze the downloads of the model checkpoints at GitHub, we see that the downloads of tissue model are twice less than downloads of the artifact model. And it indeed so that the artifact model also can detect the background, I think, pretty effectively. But actually, the intended use is that you firstly take a tissue detection model. It takes 1-2 seconds per slide, and then you don't analyze for artifacts with a second model in the areas with background. So it can increase the speed of analysis significantly. And I think that we also clearly stated it later in the GitHub repo, but I think not everyone understood it so far. And I think that important that you use a tissue detection model first to even more increase the performance here.
Oh, brilliant. Thank you very much for clarifying that, Yuri. Does anyone else in the room have any questions they'd like to ask? Next. Sure. So we've got a question from Mark. Can you one, Mark, sorry.
I'm just wondering, is it purely a H&E model, or does it work also on MIHC? Have you tried it at all on that? Would you recommend trying it on that, or purely H&E? No.
No, actually, the training data was only about H&E slides. I'm not sure. So we had some cases in this test data sets with immunohistochemistry. It was able to detect some artifacts, but I think it's not reliable on immunohistochemistry slides. So the use case here is H&E slides.
Thank you.
Is there, I guess, a follow-up to that is, as you, I guess, have all of the pipeline set up now for making this H&E tool, would there be, is it in your mind to maybe generalize it to MHC in the future, or is that?
It was difficult to hear this question. Adam, could you maybe repeat, because it's
Sure.
Came from far away?
No, of course. So Mark asked if it's in the pipeline in the future to maybe see if you can generalize this to IHC as well.
So I think we are not planning that, because we already invested like almost 2 years into this tool. And I think also that immunohistochemistry is a domain heavily populated with commercial algorithms, and I'm pretty sure that they will have QC pre-processing steps. So we're not. So our main focus actually is H&E based analysis. So I will rely here on more on commercial algorithms and commercial QC tools. So we don't plan to develop anything else.
Makes sense. Thanks.
Sure, thank you. And I also have another question. Actually, there was a slide. It was a great slide which showed that per department there was per tissue type, I think it might be actually, that there was a different area of artifacts. And I believe Zhilong said something on the lines of that it was to show that if you determined if there was too much artifacts on a slide as a result of the pipeline that was being generated, and whether you had to go back to the lab basically and do the slides again as such. And my question is how do you determine whether the area of artifacts as a result of an incorrect pipeline is actually due to an incorrect pipeline, or if it's just due to some sort of domain shift?
As we don't have a ground, or as we did not have ground truth for this large-scale analysis, we just wanted to compare the departments. We only did a visual review. So the only problem we identified was with, for example, with one of the German institutes scanned with a very old version of the 3D histech scanner. And we saw that it has some, it was not like a clearly false positive results. It was more than most of the slides had a fingerprint artifact. So it's like small bubbles. You actually normally ignore them as a human being. But we saw that, for example, we have a patch and there is this small oil drop from fingerprints, then the whole page will be overcalled as an artifact. So it increased the area of artifacts significantly, but we saw it only with one institute and one scanner. So it's clearly a generalization problem because it's like some very specific quality of image. But again, it was an old scanner. I think it was also scanned under 20x magnification. It was not a typical case like we see it nowadays with modern scanners. And also what we saw is the melanoma case. So if you have a lot of pigmentation, so we actually, it was like a year in the project, we thought, okay, everything is ready, and we can validate it. And then we started analyzing TCGA slides and saw that actually we have a significant overcalling of pigment in melanoma as an air bubble, or slide edge. So it's basically it's very similar from the visual appearance. And then we decided, okay, we make another round. So we included some cases with melanoma with pigmentation, but also it was also the case by by the renal cell carcinomas, by papillary renal cell carcinoma, they have like 5% of the cases, they have like hemosiderin pigment in the slide. So we included also these cases, so 2 types of cases, and then we retrained it once more time. And the problem was no more a major problem. So in some cases, it was like overcalling of the air bubble artifact in melanomas, but it was not that significant as in this first round. So it's still there, and the most obvious way, as we don't detect the artifacts as one class, like all artifacts as one class, but we detect these artifacts on a class basis, so that you can, in the final mask from the artifact dictation in melanoma cases, you can ignore this air bubble artifact, and it will. So air bubbles are not that common in old slides, maybe, but if you're sure that these are relatively a new slide, like 2-3 years old, and then you just exclude this type of artifact from the mask, you probably completely solve this problem. But for now, it's like it's still there. Yeah.
Oh, sure, that makes sense. Thank you. Do we have any more questions from the people either online or in the room that anyone would like to ask? No. Oh, perfect. Well, thank you very much, Jorin. Thank you very much, Zhilong, for a fantastic talk. It's been really interesting to hear about the tool, and I think it looks like a great addition to the community. So I've already started to have a go at using it, and it looks really, well, it's very fast, so that's great, and it looks like it's pretty accurate as well. So fantastic.
Thank you for the invitation.
Not at all. So I suppose one final question then that we normally ask our speakers is, so Zhilong or Yuri, if you'd like to answer this, is, so what do you think, so being this relatively early on in 2025, what do you think are going to be the major breakthroughs or the major advancements in computational pathology in over the next, the 9 months of 2025?
Sorry, but
No, I was just asking. So, what do you think are going to be the next big steps or the next big things to happen in computational pathology over the coming year?
Oh, this is a difficult question, especially for when unprepared. Yeah, so I think there are many developments, many important developments, like vision language models, multimodal approaches, and also integrating large language models into the pipelines, agentic workflows. So actually many practical use cases. I think in our lab, and Zhilong would probably agree, we don't concentrate a lot on the like training another foundation model and something like that. I think these are tools, and it's better to be on the application level, as as Andrew Eng formulated it, that then you always have what to do, and there would be some important clinically relevant tools arising. So I think we are at that level. So using all advancements now in field to make something meaningful for the clinical practice. Yeah.
Brilliant. Well, I think that's a great way to draw the seminar to a close then. Well, thank you very much, Zhilong, and thank you very much, Yuri, for a fantastic talk. And just a bit of a reminder for everyone online and in person, we've got our next talk will be on Monday, the 17th of March, so 2 weeks today. We'll be joined online by Dr. Jinxi Zhang from Stanford University to discuss their new work on the new Musk Foundation model. So hopefully see you all there. But again, thank you very much, Zhilong. Thank you very much, Yuri, for a great seminar. And
thank you, everyone.
Bye-bye.
Bye-bye.
Thank you.